Okay, so we have section 5.2, which is going to be very, very similar to what we did in section 5.1. We're solving systems of linear equations. The difference here is it's linear equations in several variables. In 5.1, we did typically x and y, but 2 variables. In 5.2, we'll do primarily 3 variables. We may look at some systems that have more than 3. And that's our primary learning target here, is solve a system of linear equations in 3 or more variables. And then we'll look at an application problem. So before we get into actually solving a system of 3 variables and 3 equations, a little bit of background. We typically, in most algebra courses, stick with this 2-dimensional plane here called the Cartesian coordinate plane, or the the XY plane. And it is helpful. We graph a lot of things on here, and we can find coordinate locations of points. But that's limiting to 2 variables, an x variable and a y variable, in this 2-dimensional Cartesian plane. When we add a third variable, we have x, we have y, and when we add a third variable z, it adds another dimension to this graph. So you can see we have this original xy plane here, but now we have a yz plane here and an xz plane here. So this is called a 3D coordinate grid right here. And not that you're going to need to be graphing any of these things in section 5.2 or any time in Math 1050, but I think it's helpful to visualize and have an idea of what's going on when we're talking about 3 variables. X and y stay in this plane, but then when you add z, it adds a dimension that comes out into space. So we have a 3-dimensional plane that we graph on. Now, locating points on the Cartesian plane, like the point, let's do black. The point 3, 2, you go 3 units in the x direction, 2 units in the y direction, and you locate the point on the plane. When you're talking in 3 dimensions, the point 3, 4, 5, 5 is this new dimension now. We would go 3 units in the x direction, and notice I got the x-axis here, 3 units in the x direction for 3, and then 4 units in the y direction here, because this is the y-axis, and then you go 5 units in the z direction, which in this case is up. So we locate points in space very similar to how we would locate points in the Cartesian plane. It's just in 3 dimensions, where we have x first, and then y, and then z. And again, like I mentioned before, you're not going to be graphing anything in 3 dimensions in Math 1050. That's for further math courses down the road. But the reason I'm going into this, we talked in section 5.1 about lines. So, 2 lines intersecting to form a point typically is the solution to a system of equations in 2 variables. That's what was introduced in section 5.1. And graphing a line in standard form like this, we've talked about this before in earlier videos, but one way you can graph a straight line is just by finding the x and y intercepts. So for example, with this line, if I wanted to find the x-intercept, I would let y equal 0. And if y is equal to 0, we would get x is equal to 2. So the x-intercept rather is 2. To find the y-intercept, we'd let x equal 0, and if x is equal to 0, we would have y is equal to 3. So there's our x and y-intercepts, and then we end up connecting them to draw the straight line in a 2-dimensional Cartesian plane. It's a similar idea in 3D. So now I've got a 3-dimensional Cartesian coordinate system here. I've got the x-axis, the y-axis, and now the z-axis is the one. And it's hard to visualize a 3-dimensional plane on a 2-dimensional flat surface, but you just need to imagine that this z-axis here is coming out of the screen and into the screen. It's just moving out in space. And then this equation, x plus 4y plus z is equal to 8, is the three-dimensional version of a line. The three-dimensional version of a line is what's called a plane. And the way that you graph that is the same way pretty much that we found the x and y intercepts of a line. So to find the x-intercept, we let y and z equal 0. So the x-intercept would be 8. To find the y-intercept, we let x and z equal 0. So the y-intercept here would be 2. And then to find the z-intercept, we would let x and y equal 0. So then the z-intercept would be 8. And this gives us points we can plot now, or intercepts rather. So here we have y-intercept of 2, x-intercept of 8, and a z-intercept of 8. And if we connect all three of these, it forms a completely flat surface that actually extends in all directions. This surface extends in all directions this way. So it ends up being more like a piece of paper, if you wanted to imagine a piece of paper. It's got no depth, but it has length and width, and it extends in all directions with a y-intercept of 2, an x-intercept of 8, and a z-intercept of 8. So that's the idea behind three-dimensional objects, in this case a plane. And if we recall from section 5.1, in 2 dimensions, when we're solving systems of equations that had only 2 variables, x and y, one option was that the lines crossed in one spot and we had one solution. That was called an independent system of equations. Another option was that the lines are graphed right on top of each other. In that case, it was called a dependent system, and there were infinitely many solutions. The third option was that the lines were parallel and did not intersect. In that case, that was called an inconsistent system. It had no solution. Those were the 3 options in 2 dimensions in section 5.1. When we have a system of equations in 3 variables, we have 3 equations with the variables x, y, and z, and these coefficients would be just different whole numbers. But all 3 of these equations represent planes instead of lines. And so you can see here some different ways that 3 planes can interact in space. We can have 3 planes interacting in such a way that they're all perpendicular to each other, forming one unique solution like this. Or we can have planes intersecting in such a way that the intersection is a straight line, and there's infinitely many points on that straight line, so this would be a case of infinitely many solutions. Or we can have the planes interacting in such a way that there is no unique combination of all 3 of them, where we can have either 3 parallel planes and there's no solution, or these 2 planes are intersecting independently with this one, so there's no unique combination, or this one here. So anyway, it's the same situations with 3 dimensions as in 2 dimensions. We can have exactly one solution where there's one unique point of intersection, infinitely many solutions where the solution is a line, or no solution. And what we need to do in 5.2 really is just practice solving system of equations that look like this here. And we're going to primarily use the elimination method that was introduced in section 5.1. So I have this example here, solving a system of linear equations in 3 variables. And we've got those 3 equations. And the way this would need to work with elimination is you can't eliminate a row of all three variables at the same time. Like you couldn't get rid of just a column like that. What you need to do is choose two of the equations and eliminate one of the variables. For example, if we look at equation 1, I notice there's a coefficient in front of y of -2. And if I look at equation 2, I notice there's a coefficient of y of +2. Those are opposite coefficients, +2, -2. So if I take equation 1, I'm going to go ahead and number these. If I take equation 1 and 2, and just perform the elimination method on those two equations, I can eliminate y, and I get 2x plus 2z equals 14. Now what that leaves me is an equation with two variables, which still I can't solve. I can't solve an equation if it has two variables, but at least it gives me an equation with one less variable. I started with three variables. I'm down to an equation with only two variables, which is a start. So we need to do this process one more time. We took two equations and eliminated one of the variables, so now we repeat that with two other equations. It can't be the same equations 1 and 2. And the key is you have to eliminate the same variable that you eliminated in step 1. So if I'm calling this step 1 here, in step 1 I eliminated the y variable. So for step 2, I would need to eliminate y variable again using two other equations. So I'm going to use equations 1 and 3 because I notice equation 1 has a coefficient for y of -2 and equation 3 has a coefficient of y of +2. Those are opposite coefficients. Now you do need to realize that it's not always going to be set up this way where you automatically have opposite coefficients. You may have to multiply one of these equations or two of the equations or sometimes all three by values in order to get opposite coefficients. It just so happens that this one is pretty nicely set up. So equations 1 and equation 3 would be x minus 2y plus 3z equals 1, and then equation 3 is 3x plus 2y minus 5z equals 3. If you do elimination method on this, the y variables cancel, and again it's important that you eliminate the same variable in step 2 that we eliminated in step 1. For step 1 we eliminated y, so in step 2 you need to eliminate y. That leaves us with an equation of 4x minus 2z equals 4. So step 1 and step 2 have resulted in equations with only two variables, but you notice it's the same two variables, x and z, x and z. So step 3 is to combine those. You combine the result from step 1 and the result from step 2 into a new system of equations with one less variable. And then you solve this system of equations with two variables, like how we solved them in lesson 5.1 using elimination or substitution. So, and again, it doesn't always happen to have opposite coefficients automatically. We're getting pretty lucky on this example. You may have to multiply one or both equations by some values in order to get opposite coefficients. But with this one, we can automatically cancel the z variable and we get 6x equals 18. So x equals 3. So now step 4 would be it's called backwards substituting. We have to take this result, x equals 3 in this case, and substitute it back into some of the other equations to solve for the other variables. Now the problem is, if I took x equals 3 and went back to an original equation, like this one, I could substitute the 3 here, but then I would still have to solve for y and z, and you can't solve an equation if it has two different variables. So once you've solved for one variable, you need to go just a step back, in this case to step 3, and use one of these equations that has x and z. If you plug in a 3 for x here, that's only going to leave you an equation with z to solve. So if I take this equation, for example, and replace the x with 3, that becomes 2 times 3 plus 2z equals 14. And then subtract 6 and you get 2z equals 8. Divide by 2 and z equals 4. Now that you have two values, or you have the value of two of the variables, now you can go to one of the original equations that had 3 variables. This one here, for example, and you could make the appropriate substitutions. 3 times x becomes 3 times 3 because x is equal to 3. We don't know y at this point, so we leave that as 2 times y. But we know that z is equal to 4, so it becomes 5 times 4 is equal to 3. And then add the 11 to the other side, and we get 2y equals 14. Divide by 2 and get y is equal to 7. So since we were able to find unique values for x, y, and z, what we have in terms of what the graph of this would look like is a situation where the planes are intersecting at one point in space, and that point is the point 3, 7, 4. So just as in 5.1 you needed to represent your solution in the form of an ordered pair, in 5.2 you need to represent your solution in the form of what's called an ordered triple, x, y, z. So 3, 7, 4 is the point at which all 3 of those planes intersect. And there is a lot of work involved in solving some of these systems of equations, so the nice thing is you can always check your work or your solution when you have a solution into all 3 systems of equations, or into all 3 equations rather. So if I'm claiming that the solution is 3, 7, 4, then this ought to satisfy all 3 equations. So if I plug in a 3 here, and a 7 here, and a 4 here, I get 3 minus 14. That's negative 11. But then 3 times 4 is 12, so negative 11 plus 12 is positive 1, so it checks out in equation 1. In equation 2, if x is 3 and y is 7, I have 3 plus 14, which is 17. 17 minus 4 is 13, so it checks out in equation 2. And for equation 3, if x is 3, I get 9 here, and if y is 7, I get 14. So 9 plus 14 is 23. 23 minus 5 times 4 is 23 minus 20, which is 3. So it satisfies all 3 equations. It is always worth checking your solutions when you're solving systems of equations, because it's very easy to make a simple arithmetic error at some point. So that's what it looks like to solve a system of linear equations in 3 variables. Again, reviewing here, step 1 is to choose 2 of the equations. I chose equation 1 and equation 2 and eliminated one of the variables y. And it just so happened that the coefficients were set up to be opposites of each other already. Again, you may need to multiply one of the equations or both of them in order to get opposite coefficients. Step 2 was to choose 2 other equations. I chose equation 1 and equation 3, and I eliminated the same variable. What that resulted in step 1 was an equation in terms of x and z, and in step 2 it was an equation in terms of x and z. So the next step was to create a system of equations using that result. It was a system of equations with 2 equations and 2 variables x and z. Solved it using elimination for x. Once I knew the value of x, I substituted directly into this system of equations that only had the 2 variables to solve for z. Once I had x and z over here, then I went back to one of the original equations here, plugged in the x value and the z value, allowing me to solve for y. And then you represent your solution in the form of an ordered triple. So now looking at an inconsistent or a system of equations with no solution. So we need to choose 2 equations here and eliminate one of the variables. And it doesn't always have to be y, but it looks like that might be the easiest variable to work with. So if I have equation 1, equation 2, and equation 3, for step 1, if I take -1 times equation 1, and then equation 2, so I'm going to multiply equation 1 by -1, because that's going to give me a coefficient of -2 right here. So -1 times equation 1 is -x minus 2y plus 2z equals -1. And then equation 2, I didn't do anything to it, so it stays the same. I'm going to eliminate the y variable and get x plus z equals 5. Okay, now when I repeat the process for step 2, I need to choose 2 other equations. I can't use equation 1 and 2, so I'm going to use equation 2 and equation 3, and I notice that the coefficients of y are not opposite. I'm going to need to multiply by a -2 here. So everything in equation 2 is going to be multiplied by -2. So I'm going to take equation 2 and multiply it by -2, and then I'm going to take equation 3. So that's going to be -4x minus 4y plus 2z equals -12. And equation 3 and when I eliminate here, y eliminates again, I get -x minus z equals -7. So now what I do is again, you take the results from step 1 and 2 and create a new system of equations. And you can solve this using the elimination method. X eliminates and z eliminates in this case. So you have 0 on the left side, but -2 on the right side. 0 does not equal -2, and this is the same thing we saw in lesson 5.1. It's not a true statement, therefore there's no solution to this system of equations. So that's what you would see if you are dealing with an inconsistent or a system of equations with no solution. Now, a dependent system of equations, this would be a system of equations with infinitely many solutions. I notice again, it just happens to be y again. It's not always y, but for these 3 examples, it seems it's the y variable is the easiest one to eliminate. But in equation 1 and equation 2, right off the bat, I notice that y has opposite coefficients. So if I take equation 1 and 2 without doing anything, without multiplying either one of them by anything, I can eliminate the y variable, leaving 3x plus 9z equals 0. Now if I take two other equations, equation 1 again, but this time equation 3, the coefficient for equation 3 in front of y is 4, and then for equation 1 it's -1, so I would need to multiply equation 1 by 4. So I'm going to take equation 1 and multiply it by 4, and then equation 3, this would be 4x minus 4y plus 20z is equal to -8. That's 4 times equation 1, and then equation 3, y eliminates, and we get 6x plus 18z equals 0. So I take the result from step 1 and the result from step 2 and form a new system of equations. And I would multiply the top equation there by -2. So that would give me -6x minus 18z equals 0. So x and z eliminate, leaving 0 on the left and also 0 on the right. This is the same exact statement that we saw in lesson 5.1, indicating a dependent system or infinitely many solutions. Now, in section 5.1, if you remember, at this point we chose a parameter t, and in two variables x and y, the convention our textbook uses is to let x equal t. When you have three equations and three variables x, y, and z, our textbook chooses, and most textbooks choose to let z equal to t. So again, it doesn't necessarily have to be done this way, but our textbook and most college algebra textbooks, when there's three variables x, y, and z, most textbooks choose to let z equal t. Z is your parameter, or t is your parameter, and that's equal to t. And if we were solving for a unique solution, once we found one of the variables, we would go back just one step to one of these equations to find the second variable. So if I substitute a t right here for z, then that equation becomes 6x plus 18t is equal to 0. And we're solving for x. We've already solved for z here. I let z is equal to t, so we need to solve for x. So what we need to do is subtract the 18t over, and then divide by 6, and we get x is equal to -3t. So there's the value for x. Here's the value for z. So we now know the values of x and z. What we're missing is y, so we need to go to one of the original equations and solve for y. So if I take equation 2, for example, and make the appropriate substitutions, 2 times x becomes 2 times the value of x, which in this case is -3t, plus y, plus 4, and then the value of z is t, and that's equal to 2. So we have -6t plus y plus 4t is equal to 2. Now keep in mind what we're solving for. We're solving for y. We're not solving for t. We already know what t is equal to. T is equal to z. We define that over here in this step. And the reason I bring that up is sometimes students get confused with what they're solving for. In this step, we're solving for y, so you want to get y all by itself on one side of the equation. So if you combine your t values here, you're going to have y minus 2t is equal to 2. If you add the 2t to the right, you're going to have y equals 2t plus 2. So what we need to do is represent our solutions then as an ordered triple. So x comma y comma z would become negative 3t for x, 2t plus 2 for y, and t for z. And that is what's considered the solution. So dependent systems, even though they have infinitely many solutions, you can still write the solution in terms of a parameter t like this. And the reason that it's necessary, I guess you could say, or that the textbook and on the exam you do it this way, is now you can use this solution to generate some of the infinite solutions that that would solve this system of equations. Remember the discussion from lesson 5.1. Infinitely many solutions is not the same thing as all real numbers. I couldn't just choose a random combination of 3 values and say, well, there's 3 numbers, so that's got to solve the system of equations. 3 comma 2 comma 5 would not solve this system of equations, but we can find ordered triples that would solve it using this parameterized solution by letting t equal different values. For example, if t was equal to 0, then we'd have a 0 on that side because t is equal to 0. Over here, if t is equal to 0, we have negative 3 times 0, which is 0. And then if this t right here is equal to 0, we'd have 2 times 0 plus 2, which is 2. So 0 comma 2 comma 0 is a solution that satisfies all 3 of these equations here. If we wanted to find another solution, we just choose a different value for t. For example, if t is equal to 1, then over here t is also equal to 1. 1 times negative 3 would be negative 3. And then here if t is equal to 1, 2 times 1 is 2, plus 2 is 4. So negative 3 comma 4 comma 1 would also solve the system of equations. And by choosing different values of t, we could make an infinite list of solutions that would solve this system of equations. But this is what your answer would be on an exam, combined with a statement of infinitely many solutions. Where did we put that? Right here. So that finishes up learning target 1, solving a system of equations in 3 variables. We had the 3 situations with a unique solution here, and the unique solution was 3 comma 7 comma 4. We had an example with an inconsistent system, no solution, because we had an untrue statement of 0 equals negative 2. And then we had a dependent system that ended up having a statement of 0 equals 0, which means infinitely many solutions. So then the very next step would be to let z equal t, and using that value we solved for the other variable that remains in this step. In this case it was x. So now x equals negative 3t, and then you take both of those values and substitute them in to one of the original equations here to solve for y, giving us this solution statement here. Now an application problem. So we have a person that's started a new diet. Each meal has to have 460 calories, 6 grams of fiber, and 11 grams of fat. So this one is going to focus on breakfast. What can this person eat for breakfast? We've got toast, cottage cheese, and fruit. How many servings of each food should this person eat to follow the diet? So since we have 3 different foods and it says how many servings of each food, it would make sense to have 3 variables. So let x equal number of servings of toast, and y could be the number of servings of cottage cheese, and z is equal to the number of servings of fruit. So if we have 3 variables, in order to solve a unique solution of 3 variables, we need to have 3 equations. We need to set up a system of equations that contains 3 equations with all 3 variables. So if we're going to have 3 different equations that contain all 3 variables, in this case toast, cottage cheese, and fruit, it would be wise to have an equation that just describes fiber of each of the 3 foods, and then a second equation that contains the fat content of all 3 foods, and then a third equation that has the caloric content of all 3 foods. So equation 1 would be fiber. Toast, which is x, has 2 grams of fiber. Cottage cheese has 0, so you could put 0y, but you don't need to because 0 times anything is 0. And then fruit has 2 grams of fiber, and according to this person's diet, they need to have 6 grams of fiber total. So this is going to equal 6. Now a second equation could be fat. Toast has 1 gram of fat. The cottage cheese has 5 grams of fat. And then fruit, it says fruit here has 0 grams of fat, so you could again put 0z, but you don't need to have 0z because that doesn't have any value. And then according to the problem here, there needs to be 11 grams of fat, so the total here would be equals 11. Now equation 3 for calories, toast has 100 calories, cottage cheese has 120 calories, and fruit has 60 calories, and the needs for calorie for each meal is 460. So this would equal 460. So what we have is a system of equations now. Equation 1, it shows only 2 variables, x and z, but it's because y is 0 in that case. Equation 2 only shows 2 variables, x and y, because fruit has no fat. And then calories, we have all 3. And this is not uncommon when we're solving a system of 3 equations. Sometimes some of the equations are missing variables, and that's okay. So we would now solve this system of equations using the elimination method, using the same steps that have been shown on the other examples. One thing we could do, for example, and this is only one of a dozen ways that this system could be solved, but equation 2, for example, already has z missing. Z has been, if you will, eliminated from equation 2, and it only has x and y. What I would do then is take equation 3 and equation 1 and eliminate z. And in order to do so, since equation 3 has a coefficient of 60 and equation 1 has a coefficient of 2, what I would need to do is multiply this top equation by negative 30. So then that becomes negative 60x minus 60z equals negative 180. And then the bottom equation, 100x plus 120y plus 60z equals 460. I can eliminate z, and then you've got to be careful and look closely. You have to combine the x variables here. That would be 40x. And you also have to be cognizant of the y. 120y combines with 0y, leaving 120y. And then you also combine and subtract right here, and that's 280. And what we essentially have done now is taken out one full step, because you notice this equation is in terms of x and y. There's no z. Equation 2 was already in terms of x and y with no z. So I can take this result from step 1 and combine it directly with equation 2 because it contains the same two variables, x, y, x and y. So if I take the result from step 1, 40x plus 120y equals 280, and combine it with equation 2, we can do elimination method now to eliminate one of the other variables. So if I want to eliminate x, for example, I would multiply by negative 40. So then what we would get is 40x plus 120y equals 280. Negative 40x minus 200y equals negative 440. Eliminate x. We have negative 80y equals negative 160. Divide by negative 80, and we get y equals of 2. And remember the way that we defined y. Y is the number of servings of cottage cheese. So according to this, if y equals 2, that means 2 servings of cottage cheese. So if I know that y equals 2, I can substitute that in for that equation now to solve for x. Remember, if you only have one variable solved for, you can't go back to an equation with all 3 variables. You can go back to an equation with only 2. In this case, we have x and y. So that equation becomes x plus 5. Instead of 5 times y, it's 5 times 2 now. And subtract 10, you get x equals 1. And remember, x, we defined x to be servings of toast. So that means 1 serving of toast. So if we have x and y, we can solve for z by going back to one of the original equations. This top equation, or the equation for fiber, was 2x plus 2z equals 6. If we know that x is equal to 1, this becomes 2 times 1. So 2z, if you subtract the 2, you get 2z equals 4. So z is equal to 2, which means 2 servings of fruit. So we have the 2 servings of fruit, 1 serving of toast, and 2 servings of cottage cheese would allow this person to get the 460 calories that they need for that meal, the 6 grams of fiber, and the 11 grams of fat.